Hey everyone, this is question number 8, and in this questions it is written that a monochromatic and linear polarized light is used in a young double slit experiment. A linear polarizer whose path axis is at an angle 45 degree to the polarizations of incident wave is placed in front of one of the slits. If Imax and Imin respectively denote the maximum and minimum intensity of the interference pattern on the screen, so what will be the visibility that has been asked in these questions? Okay, to solve this problem, let me draw a simple diagram of a young double slit experiment. So for that, we use a point source here. Then we place two pinhole in front of this point source. Two pinhole and this point source, and then at a certain distance we place here screen. This is the screen. So what is going to happen? So this point source will create a wavefront like this. And then this wave will passes through this two pinhole, and they will superpose on the screen. They will superpose with each other on the screen, and when the superpose will on the screen, depending upon the phase difference at different point on the screen, some point intensity will be maximum and some point intensity will be maximum. So how this intensity pattern look like? This intensity pattern look like this. Yeah, so this intensity pattern look like this. So here these are the point where intensity will be maximum. These are the point where intensity will be the maximum. These are the point where intensity will be the maximum, and that intensity is defined as Imax. And these are the point where intensity will be minimum, and the intensity at this point defined as I mean. So if we want to calculate visibility of an interference pattern, so what we have to do, we have to calculate this value of maximum intensity and minimum intensity. And once we know this value of this maximum intensity and minimum intensity, then we can put in this formula visibility V is equals to Imax minus Imin, and divided by Imax plus Imin. Okay, so these definitions we're going to use to solve this problem. Okay, so this is what we have shown here. This is simple experimental setup of young double slit experiment. So this is the source of light. And then this light will passes through this point slits. Now this 2 point is called pinhole. So when this light passes through this pinhole, they will create a secondary wavefront here, and when the wave will superpose at the screen, so depending upon their phase, some point intensity will be maximum and some point intensity will be minimum. So this pattern is this phenomena is known as interference, and this pattern is called interference pattern. And in this case, what will be the visibility of this interference pattern? So for that, we have to measure a maximum intensity, minimum intensity, and then we put the value of maximum intensity, minimum intensity in this formula, we get the visibility. Okay, so this is one concept we're going to use here. And second concept we're also going to use here, that is the effect of a polarizer. The effect of a polarizer, the state of polarization of a linear polarized light. A linear polarized light. That's mean when a linear polarized light passes through a polarizer, so what will going to happen to the state of polarization after passes through the polarizer? That we have to show here. That we'll see. Okay, so for that, let's say this is a linear polarizer. Okay, this is a linear polarizer, and what we are going to do here, we are going to impose a coordinate system on this polarizer. Let's say this is x-axis, this is x-axis, and this is y-axis, and this is the z-axis. Okay, so this is x-axis, this is y-axis, and this is z-axis. And what is this? This is a linear polarizer, LP. LP means linear polarizer. And we have to define path axis. So in this case, let's say path axis or optical axis of this polarizer makes an angle theta with the positive x-axis. Okay, an angle theta with the positive x-axis. So this is the optical axis of this polarizer. The path axis, optical axis, both are same. So this is the optical axis of this polarizer, which makes an angle theta with the positive x-axis. Okay, positive x-axis make an angle theta. This angle is theta. So the path axis of this polarizer makes an angle theta with the positive x-axis. So now what we're going to do here, let's consider an electromagnetic wave which is propagating in positive z direction with amplitude E0, and it's a linear polarized light. And let's say assume that the polarizations of this wave is x polarized. So how can we represent this wave? So we can represent the electric field of this wave is equals to E0. We have assumed amplitude is E0, so E0, and then it is x polarized light, so this amplitude have only x component, so E0 x cap. And let's have to write phase terms. So in phase term we have to rewrite, let's say angular frequency of the wave is omega, so omega t, and it is propagating in positive z direction. So if we assume the propagating vector of this wave is k, then we can write kz. Okay, so this will be the mathematical expressions of incident wave, which is linearly polarized light, linearly polarized wave, and its electric field is oscillating in x direction. That means x polarized linearly wave which is propagating in positive direction, and amplitude of oscillations is E0. Okay, now if this wave passes through this polarizer, what will going to happen? Other we can say what will be the mathematical expression of this wave after passes through this polarizer. So when this wave and this side, electric field will oscillate parallel to the x-axis. So electric field will oscillate like this before passes through the polarizer. So when this wave incident on the polarizer, we can say that electric field, this incident wave, will make an angle theta with the path axis. So if we want to write this component of parallel component of this electric field to the optical axis, what will be that parallel component? It will be this amplitude is E0, which will be oscillating in positive x parallel to the x-axis. So now if we want to take the component of this field parallel to the optical axis, what will be that component? That component will be E0 cos theta. Now according to property of linear polarized light, only this parallel component will passes through the polarizer, and perpendicular component to this optical axis will going to be absorbed by the polarizer. So after passing through this polarizer, the electric field will no more parallel to the x-axis. Actually, it will make an angle theta with the positive x-axis. Okay, so now electric field will make an angle theta with the positive x-axis. So now after passing through this polarizer, now electric field will be oscillating in this direction, and this angle will be theta. This angle will be theta, and the amplitude of this wave will be E naught cos theta. E naught cos theta. So now what we have to do, we have to decompose this. If we want to decompose this amplitude vector into x direction and y direction, so what will be that component? So in parallel to the x, the component of this field along x direction, it will be E naught cos square theta, and the component of this field along y direction will be E naught cos theta into sin theta. Cos theta into sin theta. So now we can write what will be the mathematical expression of this wave after passes through the polarizer. So it will be, first we'll write amplitude vector here E naught cos square theta x cap plus E naught sin theta into cos theta y cap, and then we have to write phase term. What will be phase term? Phase term will remain same, omega t, and still this wave is propagating in z direction, positive z direction, so it will be minus omega t. Okay. So this will be the electric field of the wave after passes through the polarizer. So if we know these two concepts, then I think we can easily solve this problem. So to solve this problem, let me draw this figure again. And for this case, again, I am drawing the schematical diagram of this young double slit, but in this case, I am just removing this part. I am drawing only this two part, pinhole, and which will be the secondary source for this interference pattern and this screen. So let's say these are the two sources of light. And this is the screen. Okay, this is the screen. And then in these questions, what is written? So there will be a point source, the light will come from this point source, and then this light will passes through this two pinhole, and when light from this two pinhole will superpose on the screen, they will give the interference pattern. But in this case, what has been given that we have to place one polarizer in front of this one of the source, either this or this. Let's put it here. Okay. So what we are going to do, we are going to place a polarizer in front of this source. In front of this source. And to solve this problem easily, let me again impose a coordinate system like this way. Anything up direction will take positive x-axis, out of the phase will be positive y-axis, and towards right will be the z-axis. So x, y, z. And assuming that when this light passes through the pinhole, they will have state of polarization, linear state of polarization as it is written in the questions, and let's say assume both are x-polarized light. Both will be the x-polarized light. So, and their amplitude, let's say E naught. So here it will be amplitude E naught x cap, and this wave also will have amplitude E naught x cap. Okay. Now these two waves this wave directly come from the source to screen, but this light from this source first passes through this polarizer and then it will come to the screen. So to write the net electric field on the screen at any point on the screen, what we have to do, first we have to write what will be the amplitude of this electric field after passes through this polarizer, and that is already we have written here. We have X polarized light, and if this polarizer makes an angle theta with the positive x-axis, that means in this case what we are going to say that incident wave have X polarized light, incident wave is X polarized light, and the polarizer we are placing here. In the question it is written that the path axis of this polarizer will be 45 degree. Just for general purpose we are taking this angle is theta, because sometimes in exam it is asked as a 30 degree, sometimes maybe it can change 60 degrees, sometimes it may be put theta equals to 45 degree. So for general case we are taking this angle is theta. So here the optical axis, this is the optical axis of this polarizer, and this will make theta with the positive x-axis. So when this light will passes through this polarizer, then what will be the amplitude vector? We written on the previously, E naught cos square theta x cap plus E naught sin theta cos theta y cap. Okay, E naught sin theta cos theta y cap. So that will be the amplitude of this wave after passing through the polarizer. So once we know this amplitude, we know the wave of this amplitude. So now we can write what will be the net electric field at any point on the screen. So for that, consider a point on the screen. Let's say this point, this is the P point, and now light will come, light directly will come from this source to P point, and let's say this is S1 source, S1, and this is point is S2, second source, S2. But here light will first passes through the polarizer, and then it will come to the point P. Come to the point P. So then what will be the net electric field at point P? So the net electric field at point P can be written as E is equals to, let's first write the electric the electric field, the wave which will coming from the S1 source. So what will be the electric field which will come of the wave which will coming from the S1 source? We can write E naught, this amplitude remain E naught x cap, but this phase will be different because it will travel from this point to this point. So for that, phase will be omega t minus k S1p, k S1p. Okay, KS1p. And then what will be the electric field of second wave which will passes through the polarizer? So for that, first we'll write amplitude will be E naught cos square theta x cap plus E naught sin theta cos theta y cap, and then we have to write this phase term. It will be phase term here, iota omega t. So now it will come from S2 point, so we can write k S2p. Okay, K to P. So this is the net electric field at point P. At point P. So once we know the net electric field at point P, so now we can define what will be the net intensity at this point P. Therefore, the intensity, therefore, the intensity at point P is I equals to, it will be the intensity of epsilon naught, that's permittivity of free space, c speed of light in free space, and then we have to take product of these two electric field, net electric field with its complex conjugate. Okay, complex conjugate. So now you have to put this value of this two electric field here and you have to take this product. So when you're going to put this value, you can take a look here. All the term will contains E naught and e to the power omega t. So E naught omega t and e to the power omega t and E naught will be associated with each term, so we can take it common. E naught into e to the power omega t, we can take it common, and then remaining term, what it will be x cap e to the power iota minus iota k s1p plus cos square theta x cap plus sin theta cos theta y cap into e to the power minus k s2p. Okay, so this will be the net electric field, and then we have to take product with the complex conjugate of this field. So what will be the complex conjugate of this field? E naught is real quantity, so E naught is not will remain same, E naught, and then e to the power iota t is complex conjugate will be minus to the power iota t, and then remaining term it will remain x cap. Now it will be plus iota k s1p plus cos square theta x cap plus sin theta cos theta y cap into e to the power, sorry, there will also be iota. Now it will be plus iota k s2p. So now you have to take product of these two. So when you take product of these two, what will you get? You will get a half epsilon naught c e naught square. This iota omega t minus iota omega t, they will give you e to the power 0, so that's mean 1. And then you have to take product of these four terms with each other. When you take product of these four terms with each other, what will get? First term will get 1. Second term will get cos square theta into e to the power e to the power, when you take product of these two, you'll get iota k s1p minus k s2p. Third term will also be same, cos square theta e to the power iota minus k s1p minus k S2P, and then fourth term will get, when you take product of these two terms, it will give you cos to the power 4 theta, and then fifth term will be take product of these two terms, this will give you sine square theta into cos square theta. Okay, sine square theta into cos square theta. And now what is this? If we take k common, then it will be k into s1p minus s2p, that is the path difference between two wave, and into k, that will be the phase difference between 2 point at point, phase difference between two wave at point p. So if we write phi is equals to phase difference between two wave at point p, so we can write this phi is equals to k into s1p minus s2p. So we replace this by phi, what we'll get I is equals to half epsilon naught c e naught square, and then 1 plus 2 into cos square theta into cos phi plus cos to the power 4 theta plus sine square theta into cos theta. Sine square theta into cos theta. Then take a look on these two terms. It will be cos square theta. So take a look on these two terms, what you will get, you can take cos square theta common. If you take cos square theta common, then what will get cos square theta plus sine square theta, that will give you 1. So what we'll get here, finally we'll get a half epsilon naught c e naught square 1 plus, so I'm writing this term first here, cos square theta plus 2 into cos square theta into cos phi. Okay, so this will be the intensity, final intensity. So now we have to calculate what will be the maximum intensity and what will be the minimum intensity, and that will depends on only this phi term. At some point phi will be 0, that's mean both the wave will be in same phase, and at some point they will be in opposite phase, so phi will be pi. So based on that, because of that, the intensity at some point will be maximum and some point will be minimum. So when phi is equals to 0, that's mean both the wave in same phase, then I can say cos phi will be 1, so I will be maximum in that case. So I max will be half epsilon naught c e naught square 1 plus, if you put cos phi equals to 1, then it will give you 3 cos square theta, 3 cos square theta. And when phi is equals to pi, that is both the wave in opposite phase with each other, then cos phi will be minus 1, so intensity will be minimum in that case. So what will be that minimum intensity? So again we have to put here cos phi is equals to minus 1. When phi is equals to pi, that is cos phi will be minus 1. So for that case we'll get half epsilon naught c e naught square 1 minus cos square theta. Okay, 1 minus cos square theta. So now what we get here, we get the minimum intensity and maximum intensity. So now what we have to do, we have to put the value of this maximum intensity, minimum intensity in the definitions of visibility. So how we have defined this visibility? V is equals to I max minus I min divided by I max plus I min. divided by Imax plus Imin. So if you put the value of Imax and Imin, what we ever calculate here. So from there, what we'll get 4 cos square theta divided by 2 plus 2 cos square theta. So if we remove this 2 from denominator and numerator, finally we'll get visibility V is equals to 2 cos square theta divided by 1 plus cos square theta. Okay, so this is the general definitions of visibility. So this will be the general definitions of visibility. If you put a linear polarizer making an angle theta with the polarizations of incident wave, in that case the visibility will be V is equals to 2 cos square theta divided by 1 plus cos square theta. So in exam, if examiner asks this type of questions, I'll recommend you remember this small formula. Definition of this visibility. V will be in this case 2 cos square theta divided by 1 plus cos square theta. But if you are a BSc student or university student, first semester university student, maybe in exam they will ask what will be the visibility in this case in terms of theta. So for that you have to derive this. Okay, derivation is very easy if you know this concept, how this state of polarizations will going to change when it passes through the polarizer, and how we can define the maximum and minimum intensity. So from there you can write this visibility, and for this particular problem it is written theta is equals to 45 degree. So if we put theta is equals to 45 degree, what will be the visibility? Visibility will be 2 into cos square 45, that's mean 1 by root 2 ka whole square. So it will be 1 by 2 plus divided by 1 plus 1 by root 2 square. So again 1 by 1 plus half. So this will give you 2 by 3. Okay, 2 by 3. So what will be the correct option for this problem? For this problem, correct option will be option B. Option B. Okay, option B will be the correct option for this problem. And also you can check one thing here. If both the wave have same state of polarization, that means if we do not put this polarizer, or if we make the optical axis of the polarizer is just parallel to the polarization state of incident wave, then theta will be 0. In that case V will be maximum. In that case V will be maximum, and that's why we say for maximum visibility, for interference pattern with the maximum visibility, the state of the both incident wave must be same. State of the polarizations of both incident wave must be same. On the other hand, if you put theta equals to 90 degree, that's mean if one wave is x polarized light and another wave, if theta is 90, that's mean after passing through the polarizer, the second wave will be y polarized light. So if like this, one is x polarized, another is y polarized light, so in this case there will be no interference pattern. You can see if you put theta is equals to 90 degree, this will give you 0 visibility 0, that's mean there will be no interference pattern. For that case screen will be fully uniformly illuminated. Okay, so I hope you understand what is the effect of this polarizer. So when you place this polarizer in front of one of the slits, so by putting that, what we can do, we can change the visibility of the interference pattern from 1 to 0. Maximum will be 1 and minimum will be 0. So when you change the polarization of angle between the optical axis and the state of the polarizations of the incident wave, the visibility will also get changed When theta, if you put parallel to each other, that's mean theta equals to 0, visibility will be maximum. And if you put 90 degree, that's mean if you make a perpendicular with the incident wave, then visibility will be 0, so there will be no interference. But okay, I hope you understand this problem. So see you in the next video. Thank you for watching. Bye bye.